Hi viewers, welcome to LMS Solution. Today we are going to see about a three-phase grid-connected solar PV, wind and battery system. So this is a simulation model we developed for a three-phase grid-connected solar PV, wind and battery energy storage system. So this model consists of PV and wind generation, right? So this is a PV power generation, this is wind turbine or wind power generation. Okay, so here you can see that this wind turbine is rated at 5.78 kilowatt. Okay, and it will be connected to that PMSG, permanent magnet synchronous generator. Okay, so the rating of this machine is 24 Newton meter, 300 volt at 2300 rpm, and then maximum loading is 41.4 Newton meter. Okay, and here we are measuring the speed of the PMSG, and it will be converted into per unit and it given to that wind turbine. Okay, and then wind turbine receiving three inputs. So one is the generated speed in per unit, pitch angle in degree, and then wind speed in meter per seconds. Okay, so based upon this generated speed, pitch angle, wind speed, so it will be generate the mechanical torque, so in per unit. Okay, so that should be converted into actual by using this detail of PMSG. Okay, so that means here we use 41.4. Okay, so here you will get the actual torque. Okay, so that will be used for provide the input for that PMSG. Okay, so the PMSG will receive a mechanical torque, so the mechanical torque is taken from this wind turbine. Okay, so next you can see that this the PMSG going to be connected to the universal bridge. So universal bridge is nothing but a three-phase diode rectifier. So this is going to be convert AC to DC, and here we are using boost converter. So boost converter going to be boost the voltage of this output of this diode rectifier to 700 volt, right? So here you will get around 300 to 350 volt. Okay, so that going to be converted to 700 volt. So by using this boost converter, and also this boost converter going to used for extract the maximum power from the wind energy, wind turbine with the PMSG. Okay, so for that here we are using P into MPPT. So P into MPPT going to receive two inputs. So one is the rectifier voltage, so another one is rectifier current. So otherwise we called as the input voltage of boost converter and the input current of the boost converter. Okay, so the P into MPPT, so here we have to use for condition. That means first we have to check the change in power, and then you have to check the change in voltage, and then based upon that you have to decide the change in duty cycle. Okay, same way if change in power is greater than 0, again you have to check with the change in voltage. Based upon change in voltage you have to decide the duty cycle calculation. Okay, so then here the P and MPPT will be generate the duty cycle. So based upon this rectifier voltage and the rectifier current, so it will be processed via PWM generator. Okay, so this PWM generator will be generate the PWM pulse to control this MOSFET of this boost converter in order to boost the voltage from 300 volt to 700 volt, as well as extract the maximum power from the wind turbine generator model. Okay, so then this output of this boost converter is going to be connected to the common DC bus. So next you have to see about solar PV system. So here we have solar PV panel. So here you can see that the solar PV panel single model having 250 watts, and then we are using 15 model in series and 2 parallel string. Okay, So single panel maximum voltage is 30.7 and single panel max current at maximum power point is 8.15 amps. So when we plot that IV PV characteristics for different irradiation condition, then we will see the variation of peak power here, right? So this is a variation of peak power with the change in irradiation condition. So under standard test condition, that means for 1000 watts per meter square and 25 degrees Celsius, the maximum power is around 7.5 kilowatt. Okay, so this value going to be vary according with the change in irradiation condition. Okay, so this point should be extracted from the PV panel in order to operate the PV panel to always in maximum power point. Okay, so for that here we are using incremental conductance MPPT. Okay, so that here you can see that the PV panel going to be connected to the DC bus. So this is a DC bus. So via this boost converter. So here you can see that we are boosting the voltage, right? So here you can see that the voltage of the single panel is 30.7 and we are using a 15 series connected model. So then you will get voltage around 15 into 30.7 is around 460 volt. Okay, so here we will get to 460 volt. So the 460 volt going to be boosted to 700 volt. So by using this boost converter, and also this boost converter going to be worked along with the incremental conductance MPPT for extracting the maximum power from the PV panel. Okay, so here you can see that. So this incremental conductance MPPT we created for a control the boost converter for extracting the maximum power from the PV panel. So it receiving two inputs, one is PV voltage and the PV current. So based upon the PV voltage and PV current, so it's going to be designed that means here you have to again you have to calculate change in voltage, change in current. So based upon change in voltage, change in current, so we need to decrement the duty cycle and incremental duty cycle. So here we are checking the incremental conductance condition. So based upon this condition we need to increment or decrement the duty cycle. Okay, so based upon this voltage, so based upon PV voltage and current, right? So incremental conductance MPPT will provide the duty cycle. So the duty cycle can be processed via this pendulum generator. So pendulum generator will be generate the pendulum pulse. So this pendulum pulse going to be control this IGBT of this boost converter to extract the maximum power from the PV panel, as well as to boost the voltage from 460 to 700 volt. Okay, so next we are going to see about battery storage system. So here we are using battery, right? So here we are using 12 volt battery, right? 35 battery. So each battery having 12 volt, right? And the rating of each battery will be 48. Okay, so initial state of charge we are fixing is 50. So as per this detail, right, and the voltage is 12 into 35 is around 420 volt, right? So here you have to boost the voltage from 420 to 700 volt by using this bidirectional converter. So here we are using bidirectional converter. Okay, so this is bidirectional converter. So this bidirectional converter going to be controlled by means of voltage control method. That means, so here you have to measure the DC bus voltage. So the DC bus voltage going to be compared with the reference voltage 700, and it going to be processed via PA controller, and PA controller will be generate the duty cycle, and it going to be processed via pendulum generator. Okay, so pendulum generator will be generate the pulse for that bidirectional converter to control these two IGBT. Okay, so this bidirectional converter will maintain the DC bus voltage always around 700 volt, and also this bidirectional converter will be used for change the direction of the current flow in this manner, right, according with the power balance in the system. Okay, if there is excess power in the system, then battery going for charging mode. That means if consider load, right, we are using DC load as well as AC load, right, DC load in the DC bus system, AC load in the grid side, right. So if the power generation from the PV and wind, right, is greater than that DC load and the AC load, then that excess power will be going to used for charge the it will be charge the battery. Okay, it will be charge the battery. If suppose this DC load, that means DC loads, yeah, that means power generation from the PV and wind is less than DC load and AC load, then battery will be discharged. Okay, so battery will be discharged during that condition. Okay, so next you have to see about three-phase grid integration, right. So here we have that three-phase grid and along with the three-phase inverter. So in DC bus we are going to connect this three-phase inverter. So here we are connecting that three-phase inverter. Okay, so and then the three-phase inverter going to be have LC filter in output end. After LC filter, so that output of this LC filter going to be connected to the three-phase source, and then here we have three-phase load. Okay, and then this inverter, right, so this inverter going to be controlled by means of DQ current control concept. Okay, so this inverter going to be controlled by means of DQ current control concept. So for that we are going to measure the voltage across this capacitor, right. So we are going to measure VA, VB and VC, and also the current from the main output of this inverter, so like IA, IB, IC. Okay, so first we need to generate the sine cosine, right, that means sine wave cosine wave. So based upon that and the voltage across that capacitor, otherwise we can call it as a voltage across that three-phase grid. Okay, so based upon the grid voltage, okay, we are going to generate the and sine and cosine. Okay, so next you have to generate the reference current. So reference current here we are going to generate, so based upon two things. One is PV current and the SOC of the battery. Okay, so because we are going to control this inverter in current control mode, right, so for current control mode we need to generate I reference. Okay, so we need to generate I reference. So this I reference will be generated based upon IPV and the SOC of the battery. So here we have the condition, if IPV that means PV current, right, is less than 0.5 and the SOC is less than 10%, then we are going to get the power from that grid. Okay, so we are going to get the power from the grid. So here we are fixing I reference equal to 10. If suppose this IPV is greater than 0.5 amps and the SOC is greater than 10%, then we are providing power to the grid, so with the reference current of -5 amps. Okay, so this is a concept, that means, sorry, yes, we are going to provide power to the grid with the current of 5 amps. Okay, so here we will get a higher reference current, that means here we will get the magnitude of that current. Okay, peak current of that three-phase inverter. So here you can see that, so we are measuring the output current of the inverter, so that going to be converted into DQ form by using APC to DQ conversion, nothing but a power transformation. And here we are getting the ID reference. Okay, so this ID reference going to be considered as a D reference, ID reference. So here we are going to control only real power, is not reactive power, so that's why IQ reference we are consider as 0 here. So after that it going to be processed via current controller. Okay, the current controller for a D axis and current reference for a Q axis. Okay, so after that we will get the controlled voltage from that current controller in the form of D and Q. So that going to be converted into ABC by using inverse power transformation, and here you will get the controlled voltage in the form of ABC. Okay, so then this M1, M2, M3, right? So going to be processed via this PWM generator. So here we are using 3 PWM generator with comparison with the triangular wave. So then you will get 6 pulses. Okay, so this 6 pulse going to be control this inverter. So automatically according with the reference current, right, I reference current, right, the current of this inverter can be controlled in the system. Okay, and then I am going to explain the condition. So here we are making the wind speed. So initially from 0 to 2 seconds the wind speed will be maintained at 12 meter per second. After 2 seconds it comes to around 10.8 meter per second. And here we are making irradiation, right? So every 0.3 second we are changing the irradiation from 1500 10, and then again comes change to 500 1000. So we are creating the dynamic changing irradiation wind speed condition. And here we have DC load is around 2.5 kilowatts, and then here we have AC load around 2 kilowatt we are using. So based upon this condition, so the power sharing will be happen in the system. I will show you the result. So first I am going to showing that the PV measurement. So this is a PV measurement. Next I am showing battery detail. Okay, so this battery. So next I am going to open DC load measurement. So this is a DC load measurement, and then so this is DC bus currents, right? And then I'm going to open power of wind side converter. Okay, and then this is AC load voltage and current, and then this is grid voltage, inverter current, and grid current. Okay, so here you will see that, right, for initially that power will be around irradiation will be 1000 watts per meter square. So that's why we are getting around 7.5 kilowatts. Okay, for 500 watts per meter square the PV power is around 3750, and then for 10 watts per meter square the power around 0. So again that irradiation changed to 500, so that's why it comes to 3750 watts, and then here you can see that it comes to 7500 watts after changing the radiation. Okay, and then here you can see that for a 12 meter per second we are getting around 5.7, right, 5.5 kilowatt from that system. And then this is battery voltage. This battery voltage maintained around 450 volt or 430 volt, and then this is a current variation according with the change in PV power, right? So here you will see that when PV power having PV and wind having excess power, then battery goes for charging mode. Okay, when PV power is comes to 0, that is comes to discharging mode. Okay, and here you can see that the DC bus voltage maintained at 700 volt, and the DC load current is around 3.5 amps, and then here you will get DC current, that means DC power is around 2.5 kilowatts, right? And then this is a AC load voltage and AC load current, right? And then this is grid voltage, so this is inverter current, so this is a grid current. Okay, so here you will see that grid inverter current, right? Inverter current peak amplitude is maintained at 5 amps, because now the condition, right, the condition is IPV is greater than 0.5 and SOC is greater than 10%, so that's why that peak current is maintained 5 amps. Okay, so when the condition is when SOC is less than 10% and IPV is less than 0.5, then we are getting power from the grid. And here you can see that the this is a PV and wind converter current. Okay, so this is battery and DC load current, and this is inverter input current. So three phase input inverter input current, right? The sum of this all current, right, at the node point, right, which is equal to 0, right? So here you will see that the power balance, right, the power balance between source and load will be maintained. Okay, so that means here you can see the sum node point, right? In node point we are connecting wind, PV, battery, and then here we are connecting inverter and DC load. Okay, so this current, right, wind, PV, and then this is DC load, and this is inverter. So battery, it may be changed according with the direction, right? So now I am going to consider as inward direction, right? Sum of this current always should be 0, right? So here you can see that the sum of current at DC plus always 0. So what's this is implies that mean inference of this condition is, so and the power balance always maintained, okay, in this system, okay, for change in irradiation condition as well as change in wind speed condition. So this is working of three-phase grid connected PV wind battery energy storage system in MATLAB. Thanks for watching our videos. Kindly subscribe our channel and also click bell icon for notification about upcoming videos. Thank you so much. Bye bye.